Hi folks. Hey, I'm doing this kind of at the end of the video, but I'll probably put it up towards the beginning. I want to thank you all for all your comments about seeing my face on the last video. I didn't really realize that was a big deal, but well, here it is, for what it's worth. I have to look at it every morning when I get up and look in the mirror, so not a big deal to me. But anyway, as you can hear, the amp is playing. I'm just kind of burning it in a little bit. And what I'm going to do is I'm going to use my my Zoom digital recorder and see what kind of recording we can get of this. We'll put it at the end of the video. You see the little setup we have here. I don't know if I got it on camera. There we go. And you can see, pretty nice. And I'm pretty happy with the way it turned out. So let's get this done. Let's get this video edited and put together, and we'll see you real soon. I wish you all peace, joy, happiness, and good health in your lives as always. And next project, we got 2 more projects. They'll be down in the wood shop. We're going to build a case for this amplifier, and then I have a set of speakers I picked up from a seller, and we're going to refurbish those and recone the woofers and do some things like that. And so it should be some interesting things coming up. Take care, everybody, and we'll see you next time. Bye-bye. Well, we're up early this morning, and my wife just brought these rugs in from the... Hey, wake up. Brought these rugs in last night from hanging on the line to dry. Bathroom rugs. And this one took full advantage. Don't be looking all innocent. So you might ask, what do we need all these rugs for? Well, I'll show you. Huh, Bella? You're busted. Good girl. Wipe your feet. Hi, everybody, and welcome to our next part of the X-101-C Fisher integrated amplifier video. So this mess you see on the bench is an attempt to make some measurements that are required by the service manual for this amp. And if I get this page out, you can see it's a relatively small procedure. The first procedure is very straightforward, and that is they want you to take a volume control to minimum, take a DC voltmeter, and they want you to connect it to pin 5 of any of the output tubes. All the output tubes here, all these 7591s, are all, the cathodes are all tied together. So you're really measuring the cathode voltage with respect to ground. And you adjust this little bias pot right down in here until you get 40 volts. Very easy. I did that off camera. I think it's pretty easy. Now, one thing I did do, I don't like drilling holes in vintage equipment, but I did make one exception for this amp, and that is getting onto that pin is kind of difficult. You have to flip the amp on its side or upside down. It has to be powered up. It's kind of finicky. So what I did was I took a just one of these little banana jacks right here, and I just fitted it right there in between 2 tubes. I drilled a small hole, and I attached this to pin 5 of one of the output tubes, and then that gives us a convenient test point on the back here to get our 40 volts. That's all I did. Now, the more interesting part is the way that you adjust the phase inverters on this thing. And the phase inverter is a cathodine style, or concertina, however you want to call it, which these don't really have much in the line of gain, but they are very linear. And you can see we have one tube that handles both channels. And the idea is the way this is going to be biased, if it's biased properly, is that you want this thing to swing positive and negative in the cleanest way possible. Now, you'll never, if this is properly designed circuitry, you'll never hit the rail voltage on either direction. So you'll never you'll never shut the tube off and you'll never fully turn it on before the output tubes actually clip. So the idea is to get a signal here that can go higher than the maximum signal required to drive this into clipping. So that's never an issue. What is an issue, though, is if you get too much asymmetry in that, it can affect the distortion properties of the tube or of the output section. So the way Fisher handles this is they put this potentiometer right on the B+ voltage, and they drive it right into this little this pot here, and basically you're adjusting the B+ resistor, your anode resistor up here. And in order to do that, they want you to adjust it until you get minimum intermodulation distortion. So in order to do that, they want you to use an intermodulation distortion analyzer, which I do not have one. So what I attempted to do is I thought I'd do some experimenting on this and kind of see if we can make these adjustments using just some basic tools, some software that we can put on a computer, using our computer, and then using a audio player, this is the best one I've got as far as noise and distortion and everything. It's a pretty nice unit. And I created a file, and it is a lossless file, and it consists of 2 test tones, and we'll get into that in a little bit here with how this works. And so just using my audio player and my computer and the scope to some degree so I can kind of see what's going on, we're going to see how we can adjust this. Now again, I'm not going to get an IM distortion figure, although you can measure the spectrums, add them all up, and you can actually do a little math formula to figure out the percentage of IM distortion. But I'm not going to do that. I'm not interested in it. I'm just interested in minimizing it. So let me go over my setup. Hopefully, I think some of you might get a little bit lost in this. Some of you may be beyond what I am with this and actually have your own methods. And everything in between. So I kind of give you that up front. So let's start. So the first thing we want to know is, what device are we using to measure this? Well, I'm going to use an audio spectrum analyzer. Now, if you have an audio spectrum analyzer, there were ones made a long time ago. They have, phosphor, CRT monitors. They almost look like an oscilloscope, but they're a spectrum analyzer, a special type that can look at audio frequency, 20 hertz to 20 kilohertz. My spectrum analyzer is designed for RF. Therefore, the lowest frequency it can measure is 9 kilohertz. It can't measure anything below that accurately or at all. So what we're going to use as a little program, I don't want to move my camera around too much, but it's a little program down here called True RTA. And you can go online and you can look it up. I think there might be a freeware version, and then there's also more advanced versions that give you more resolution. In other words, the higher the resolution you want the program to be, the more you pay for it. But it's really not a very expensive program, because this is actually a little kind of an all-in-one program. The more I'm using it, the more impressed I am with it. Again, this is not an endorsement. Nobody paid me for it. I looked it up. It suited a purpose. I downloaded it and purchased it, and I'm just telling you my experience so far. The nice thing about this, it does have an audio generator, and it can do sine, square wave, triangle wave, sawtooth, impulse, pink noise, and white noise, which is pretty decent. And it uses your sound card in your computer to do that. It also uses the input of your sound card as a test point to connect devices, and there's an oscilloscope in this, so you can use it as like a digital oscilloscope. And more importantly, the main thing is it is a audio spectrum analyzer, which is really good. So we're using the spectrum analyzer function in this, and we are not using the audio because we need a very special audio signal to check intermodulation distortion. Don't confuse that with TIM distortion that we were talking about on the Sansui AU-X1 videos. This is just plain intermodulation distortion. So here's the way it works. The first thing we have to do is they want you to measure the IM distortion at the speaker terminals. And they want you to terminate this amplifier at 4 ohms. So I have two 4 ohm resistors. These are way overkill. This is a 28 watt amplifier. These are 1000 watt 4 ohm non-inductive resistors. Why? Well, I have them, and my little resistors that I have, if you leave them on for any length of time without a heat sink, they get kind of hot. And these ones won't heat up. I can run it all day long at full power, and these won't even get warm. So very simple. You take a 4 ohm load, you put it across the 4 ohm and common terminals of the amplifier, and so you're putting a non-inductive load on there, and a non-reactive load. The next thing you have to do is you have to get a sampling of the output across this resistor and send it into your audio card. Now I'm using an audio interface. I'm using a PreSonus Audio Box USB 96, and it can do up to 96 kilohertz bit rate, which is really good. And it's a very good, it's kind of like a mixing console. It has 2 channels, and it will do microphone, line level inputs, all kinds of stuff. But you can just use the sound card built into your laptop computer. It would be just the same. Some sound cards do not have the bit rate of others, but most of them do. So you don't need to go out and spend money buying that. Pretty much your laptop computer or your sound card in your desktop computer will work just fine for what we're doing. Now the next challenge is they want you to put 8 volts. So 8 volts into 4 ohms is going to turn out to be a 16 watt signal. So you're going to have 16 watts of power at 8 volts RMS. 8 volts RMS is way too much input for your computer. It will damage the input of your computer. Do not hook the speaker terminals directly to the audio input terminal of or jack of your computer. You will damage it. So first thing we need to do is we need to attenuate that signal somehow. So that's what this little box is. And all this is a 68K, 68,000 ohm resistor in series with a 10K potentiometer. And then I use the 10K, and the 10K goes from ground, or from the common side, to the resistor, and then the other end of the resistor connects to the positive terminal. So it's just a series circuit. And by adjusting this, and then the output here, which is just a little RCA jack, is connected across the potentiometer. So by adjusting this potentiometer, I can adjust the ratio of how much attenuation I want. And then I took 2 little marks, and this would be a 10-to-1 ratio, and this little black mark is a 20-to-1 ratio, roughly. And then that way we can have a safe low-level signal to feed into our amplifier. Remember, we don't really care about accurate voltage going in. We just want the range to be accurate. Everything will scale from that. Okay, the next thing we need is the correct type of test signal. And the test signal that we're going to use is called the SMPTE, SMTPE, or DIN type test signal. And that test tone is comprised of 2 different sine waves. You have a stimulator sine wave, or an exciter sine wave they call it, and that is going to be 60 hertz, and let's say that it's at 0 dBV, so that would be 1 volt. And then you're going to have a second not harmonically related signal that's higher frequency, and it's at 7 kilohertz, and it's going to be 12 dB down from the 60 hertz signal. So that means it's going to be 1/4 or 1/4 of the amplitude of the 60 hertz. So that 60 hertz combined with that 7 kilohertz is going to create a bunch of beat frequencies, and they're going to be all kind of weird frequencies that are created from those two frequencies colliding with one another. It's going to cause disharmony. So unlike harmonic distortion, harmonic distortion is always going to be an odd or even number of the fundamental frequency. This is going to cause all kinds of distorted noise, and it's doing that for a purpose. The idea is, in a perfect world, you would see on a spectrum analyzer, you would see two signals, two frequencies. You would see the 60 hertz at a higher amplitude and the 7 kilohertz at a lower amplitude. And then together, as they collide and beat against one another, they would create beat frequencies that would almost look like an amplitude modulated signal. So you'll see an upper and a lower sideband, we call that, of that frequency. Now what we're interested in, again, the 60 hertz is there to create all this mess. The 7 kilohertz is the one we're actually going to look at. So we want to zoom in on that 7 kilohertz signal and look at the sidebands, and then look at all the surrounding frequencies with it. Now you're going to see a whole bunch of things, but they're all going to be much lower amplitude than all the others. And the name of the game here is to adjust those pots until we get a minimal amount of secondary noise frequencies. So that's what we're going to do. We're using that tone. I created that tone on Audacity. So Audacity is a freeware that you can download. It's an audio program. Most people use it to record things, but there's also an option in there to create a tone. And I created two tones, and then I mixed them together. And then I saved it as an audio file. And that's what I'm playing through my audio player. So that gives you an idea of what we're doing. So let's kind of demonstrate, and it'll kind of make sense. So according to the procedure, they want you to adjust about 8 volts across the 4 ohm load. And they're talking 8 volts RMS. So I have my oscilloscope also connected, and I have a measurement set up there for RMS voltage. And we're just going to turn up the amplitude of this signal until we get to 8 volts RMS. Once we do, we're going to turn our focus to the spectrum analyzer, and we're going to look at what happens. Now watch the spectrum analyzer as I bring the amplitude up. So we're turning the volume up, and you can see down here is 50 hertz. So 60 hertz would be this line right here, and there's 5 kilohertz and 10 kilohertz. This would be 7 kilohertz, and you can see already you have some sideband activity, but on our 7 it's pretty clean. As we increase volume, you're going to start seeing the sidebands come up, and you can see they pop in after a while because the amplifier is starting to create that intermodulation distortion in a level that we can see it. So now we're at 8 volts, and we can see a whole bunch of harmonics and things that are being created, and beat frequencies created by this. This is normal. You're going to see this to some degree. And the name of the game is to adjust it until you minimize all these little spurious noises along here. So by turning this pot, where am I at? I can adjust this pot and watch some of the lower ones. You're going to see them come up. See how they're going up in amplitude? And you'll kind of go through a null point when you adjust this, where there it's kind of nulled out. Now it starts, other ones start creeping up. So it's kind of a balancing act. And right about there is pretty good. The other thing is we don't want more sidebands coming up on either side of our 7 kilohertz. Now we can also zoom in on that. But that's channel 1. Let's move over to the other channel, and we're going to look at it and kind of compare it. We're now on the other channel, and let's bring up the amplitude. And as you can see, there's a lot of crap going on there. So this one has got all kinds of stuff going on, right? And some of this is not the frequencies. Some of this is noise in that channel. So we can try to adjust it. And you can see it doesn't really make a whole lot of difference because there's so much noise. So this is showing us that there's noise in that channel. And you could see our waveform is kind of jumping around. You remember how thick the waveform was because it looked like an AM signal? Look on this one and it's not there, or it's, you know, it's very, very small. So that this peak is much lower. So there's something going on with this channel is what this tells us. So this is a really good test. This is stuff that you may not hear with your ears unless you're really critically listening, and by then you've already got it wired up to your system and your good speakers and everything. But on the bench, I can tell you that if all we did was feed a single tone in there, a single sine wave at 7 kilohertz, it would look like a 7 kilohertz sine wave. You really wouldn't know what's going on in the background. So what could it be? Well, it could be capacitors, although I don't think so. It might be. It could be a resistor that's out of tolerance. So you have a voltage that's incorrect in one of the stages. It could be one of the tubes. One of the vacuum tubes is actually microphonic or noisy or something. And you can tap these. And I'm not seeing too much popping up on there. So there's several things it could be, but we do know now that the channels do not perform exactly the same. The other problem with this amplifier is you cannot bypass the tone circuit. So you have the influence of the tone circuit. If there's something wrong in there, again, one of the capacitors or one of those little couplets is bad, has a leaky component in it or an out of tolerance component, it can cause that. So we're going to try to troubleshoot this, and then we're going to come back and see if we can get that noise level to look a little bit better. But if we turn this one up, it's pretty obvious that it's not the same. You see all that noise there, and then we move everything back over. Move our scope over. Move this over. And we check it again, and you see how much quieter it is as we go up. And you see how much thicker that's the way it should look. Only with just a few spikes here and there. So definitely something going on with that channel. So now we know what we've got to do. Okay, it seems like the error was Tony and not the amplifier. Let me explain. First thing was this amplifier, the balance control pot is really bad. And the way they do it is instead of having one single pot, there's two pots that are ganged together on this. It's a dual pot. One half of the potentiometer, you know, the one front one controls the left channel and the rear one controls the right channel, so forth and so on. And basically the carbon on the carbon tracks on that potentiometer for the balance, they are no longer matched. They've drifted in value. And that's after being cleaned and all that other stuff. So I had to adjust the balance pot until both channels were performing equally. That really skews your results big time because the volume directly affects that IMD test. The other thing was the input gain on the two channels of my audio interface. One of them, the gain was set at minus 10 dB, and the other one, the gain was set at 0 dB. So there was a big difference there too. So by the time all those signals got changed around, it changed the actual signal on the spectrum analyzer. So now we have everything done correctly. Let's go up to our 8 volts RMS. And I'm going to leave this in the video because I'm still learning this software and everything, and hopefully this will, if any of you get into this, it'll prevent you from making the same mistake, hopefully. So there's my 8 volts. And you can see how clear that is now. And when you adjust it, you can kind of see how that comes way up. And then when I adjust it back down and hit that null point, it goes right out, and then it starts to come back when I go through the null point. So look at that. That's beautiful. Okay, let me move over to the other channel now. Let's put our 8 volts back up. There we go. Okay. And once again, we null it out. And you can see that's too much. This one's pretty touchy. There it is. And you see how nice and quiet it is. So really all you see is your side bands over here. All these strange harmonics. I'm not going to call them odd harmonics. They're strange harmonics. They're non-mathematically multiple harmonics, like on the harmonic you would get on harmonic distortion of a sine wave. So there you go. This amp is just quiet as a church mouse. It's unbelievable. So that's all it really was. Now I'm going to have to address the volume, and the other thing is the volume pot does not go up and down linearly either. It jumps all over the place, and it's not from noise. It's because, once again, the carbon tracks inside that pot is they've drifted in value. That's one of the problems when you have these carbon potentiometers that are used, regularly in amplifiers, which is why the higher end systems go with a stepped attenuator. The other thing I notice is running this thing at high volume for long periods of time, it does heat this thing up. This transformer, the power transformer especially, is very warm to the touch. I mean, really, really warm to the touch. And these are pretty warm to the touch. And this transformer is notably undersized for what you're asking it to do. That's one of the things. The 500C that I had, the transformer was much larger, and really that tuner didn't draw a whole. Well, the tuner did draw a lot of current because of all the filaments and all the tubes, but and it ran pretty hot too. But this one's a little bit warmer. But again, I'm running it really hard with a continuous signal at high volume for long periods of time. So, of course, our little dummy load's nothing. So anyway, we've got the adjustment done. The amplifier's working perfectly. And I think it's time to do a couple of other audio tests on it. And we're going to try to go back now and look at our THD. Now that we have this all set, our THD, our harmonic distortion, should look really good. So let's check it out. All right, we got the meter set up. We have our THD analyzer down here, and we have our RMS voltage meter up here. So this is going to actually measure RMS volts output to the dummy load. This is going to measure our total harmonic distortion. And down off screen, I have the oscilloscope set up, and we're just looking at a 1 kilohertz sine wave. And we're going to crank this up. There's your 8 volts that we were looking at, right? And you can see 0.3% THD, which is pretty good for a tube amplifier. And we're going to keep going up. There's clipping. There's just below clipping, so it's about 9.5 volts before clipping. Take it up till the distortion hits 1%. At 1% we're getting about 10 volts, and that's into that's 25 watts because that's going into 4 ohms. So if we take 10 squared divided by 4, that gives us 25 watts. So at 25 watts we're getting right around that 1% distortion, and I kind of believe that. That's about all you get out of these. So really this is a 20 watt amplifier, you know, if you want really clear sound. And there you have it. And again, I have kind of everything hanging around here. It's a big mess, but that's not bad at all. And if we drop around 9.8 volts, distortion drops way down to 0.4%. That's pretty good. Not bad for a old tube amp that's just had the power supply rebuilt and nothing else, and just had a adjustment done to it. Okay. The next thing we're going to look at now is our square wave. We want to see how much ringing we have. And you can see lots of power there and very little ringing. So let me change this a little bit. I just want to kind of see what kind of rise time. That's not bad. Not bad at all. And it rings a little bit as you start really maxing out around 11 volts. But great. Excellent. So now we'll go ahead and we'll do our frequency sweep. We'll turn that up. I just want to see how it holds. And you can see it's staying pretty flat all the way. And we're going from 20 hertz to 20 kilohertz. And it's holding up really well. Now I'm not running this at super high volume. Right now I'm just seeing frequency response. And that's pretty good. Last but not least, let's check our low frequency. I have the signal generator set at 25 hertz, which is pretty low for one of these little amps. And let's get the scale a little bit more reasonable. Look at that. All right. And you see how this really changes at low volume? And part of that, again, is the volume and the balance pots. And I believe bass and treble are also, if you notice, they're kind of not tracking either. You see, I just turned the bass knob and you notice how it made them a little more balanced. So not only do we have issues with the volume pot and the balance pot, but also the tone control pot. I don't know if the capacitors in the tone stack are bad. That's another thing to look at. We would have to actually scope the input to the tone control section and then the output, but the amplifier itself is certainly capable of reproducing this frequency pretty well. So, and there's your 8 volts. And it really breaks up pretty quickly when you get around 9 volts. So you see how I'm moving the volume knob, and you can see how they're moving independently of one another. So that's not good at all. So anyway, other than potentiometers, the rest of this amp is, I mean, it's perfect. There's nothing else to do to it. So let me see what I can do about the pots, and I think this amp will be about done. Alright, we're doing the handheld camera right now. So I have been listening to this amplifier for quite some time now. I tried a few songs out that unfortunately, because of all the copyright things, I can't play for you. But I do have a YouTube library song, and another one of those, that we're going to listen to. And as you can see here, I got this thing hooked up. Let me get the microphone flipped around here. Am I making all kind of noises? I'm sure I am. So here we are. It's all hooked up. I have the player connected up, and let me cue up the song.